Hi YouTubers, Dave out in Western Pennsylvania, USA. Continuation of our work with, as we define it, dry and wet graphite materials in a circuit with a 3.7 volt lithium-ion secondary cell. We have this circuit in with an electronic load device, ZKE Tech. The dry graphite material, in this case, it will be graphite felt, commercial material. The dry run, which I'm not showing you here, but I'll post the data, simply had a piece of commercially available graphite felt, not cleaned, used directly as is, so it could have oils on the surface, insulation, right? So we ran 50 cycles of charge-discharge with the circuit containing the lithium-ion secondary cell, because we're interested in how the graphite materials will perform after a series of 50, 75, 100 or more cycles of charge-discharge. We want to bring it up to the voltage that the lithium-ion cell is brought to. We generally charge it up to 4.1 volts. Then, of course, there'll be an initial resistance. It'll drop, the potential will drop. We take it down to 3.0 volts and cut it off for safety. We don't want to destroy the lithium-ion cell. And then we do a series of charges-discharges at a hefty 750 milliamps, and we allow rest periods of 1 minute after each charge, constant voltage with trickle current down to a cutoff of 0.20 amps. And then we discharge at constant current, 750 milliamps, down to 3.00 cutoff. We're interested in the Columbic balance, comparison of the capacities, milliamp hours, before and after each cycle. Now, what we're showing you here is the results of 75 runs. You can see the data input, parameter settings, and on the top, each step. So this is the completion of 75 runs. Took 17 hours and 15 seconds short of 41 minutes. This is simply a piece of graphite felt, but we did one extra thing. We sprayed that felt with a light coating of Aerosol Industries dry graphite lubricant spray, aerosol spray. Now they say to allow 1 minute to dry, and 1 minute is certainly not enough because I can smell the small amount of polymer used for adhesion. So I left that overnight. We'll do more careful runs. This is a preliminary run. But I wanted to apply some aerosol delivery of graphite to the graphite felt. I thought perhaps it would add a little bit extra surface area. This is what we're studying, nickel plating, and also, in this case, aerosol delivery of some graphite to a graphite surface that pre-exists. Okay, so we ran 75 cycles dry. I left the treated felt to dry overnight at 20 degrees Celsius before using it. We keep them in these small, they're convenient for bench scale plastic cases. These are called GUM and commercially available plastic dental floss sticks. And these little containers are very, very handy. Incidentally, these cases will not dissolve in dimethylformamide. And we ran the FTIR, which I will be uploading. We want to identify the polymer or copolymers here. I wrote to the company, but they did not get back to me. It's a Swiss company. And we already ran the FTIR, so we'll turn our attention to identifying the composition of this plastic container. But it's handy for bench scale preliminary work. Now you can see I have in this one the graphite felt, but also, what you're seeing, also a section of activated carbon foam. That also was sprayed with graphite aerosol, front and back, 2 or 3 times, and I let it dry. And I have that in there as a candidate material to apply a deep eutectic solvent and electrolyte, and then I pressed them together. And I wanted to just see the effects of having the graphite felt with some graphite treated activated carbon to boost surface area. I was curious how it would behave. This, in turn, the leads are secured with metal clips, stainless steel clips as current collectors. And then we solder it to a cotter pin, and that gets inserted into the circuit through the negative lead, so we can carry out charges and discharges to see how the Coulombic ratio will turn out, as evidenced by measured milliamp hours capacities for each cycle. Okay, so after we ran it, it was pretty good. Let me just show you. I'm going to be uploading the various values at selected cycles. So you can see it started off and there was some variance in the beginning, but it settled down and was very consistent for most of the cycle. The Coulombic ratio, which is very important, so we're not really losing any heat. Now what you're seeing here is not the dry run. This is a wet cycle run, very important. We treated this graphite and the foam, the activated carbon, which was graphite sprayed. We applied a deep eutectic solvent, and that solvent was the very easily prepared and well characterized choline chloride urea deep eutectic solvent, a 1:4 molar ratio respectively. We were able to dissolve in it not just lithium tetrafluoroborate electrolyte, much more expensive, but cheap pre-dried lithium bromide as electrolyte. And it dissolves. Little bit of stirring, and at 20 degrees Celsius, we can get it to dissolve in about 5 or 10 minutes. And we give it a gentle amount of warming, very small amount of warming, but it goes in very, very easily. And what concentration did we use? 18% lithium bromide in a total of 2.75 grams of the deep eutectic solvent solution. So there's 18% mass of the lithium bromide. So that is what you're seeing here, the 75 cycles. The dry run was just a preliminary 50 cycles, and I have the data. And the Coulombic ratio is pretty good. Now we're seeing some mass increase after the dry run and after the wet run. And that's because the unit is not sealed for safety reasons in this preliminary run. Here was the wet run. You could see it was open to the atmosphere because in our initial studies, we want to make certain for safety reasons everything's okay. But certainly looks a little better there, but still open. So let's keep that in mind, that it was not entirely sealed. Now we are working, let me show you this. we are working on modifying the system using different current collectors. You can see them in there. And this is a much better closure. It's in a plastic container. But in future runs, we will ensure that we have a reasonably sealed container. We don't want any moisture getting in there. So we did the wet run. And we'll be uploading the capacitances for charge discharge, but the numbers were very, very, very positive from beginning to end. So we'll have this in the data section. I'll also have my website there. And this would be the first run of a DES containing lithium bromide, where we carry out 75 cycles of charge discharge. And we're certainly not seeing loss of solvent. We'll keep you posted as we progress. Incidentally, here is the activated carbon foam that we use. It's commercially available. And it's just one material we want to look at as a potential separator in assembly of a supercapacitor. That's actually what we're interested in. We're doing preliminary studies of the graphitic material electrode candidates and DES ionic liquid solutions. But I wanted to run a section of this. But I actually have been having good luck spraying graphite on paper to use as a separator in a supercap assembly. But that's another story at another time. Thank you for watching. Bye for now.